Imagine you could bend the fabric of space itself, compress the emptiness ahead of your ship, stretch it behind you, and ride a wave of curved spacetime to another star without ever breaking the speed of light. In 1994, a physicist proved this idea works on paper. The math is real, the equations balance, general relativity genuinely permits it. And that is the most terrifying part of this story. Because when you look closer at what this theoretical engine actually requires, you do not find a shortcut to the stars. You find a trapdoor into the deepest rules the universe enforces. Rules about energy that does not exist, causality that shatters, control you can never have, and arrivals that destroy everything you came to find. If you enjoy journeys that challenge what you thought was possible, go ahead and hit that like button and subscribe. It genuinely helps the channel grow. Now brace yourself. Let's begin. The closest star to our solar system is Proxima Centauri. It floats 4.24 light-years from Earth. That number sounds almost manageable until you translate it into a distance the human mind can actually grasp. 4.24 light-years equals roughly 25 trillion miles. Written out in full, that number stretches across the page like an accusation. 25 followed by 12 zeros. Now try to feel that distance rather than just read it. If you could board a commercial aircraft and fly at cruising speed toward Proxima Centauri without ever stopping, without refueling, without sleeping, without aging, the flight would last approximately 5 million years. When you departed, Homo sapiens would not yet exist in their modern form. When you arrived, every civilization that ever built anything on this planet would have crumbled into geological sediment and been recycled by tectonic forces into something unrecognizable. The pyramids, the Great Wall, every satellite, every city, every language, all of it gone before you were halfway there. And remember, Proxima Centauri is the closest star. It is the nearest possible destination for interstellar travel. Everything else is farther. Let us try another way to feel this distance. Light is the fastest thing in the universe. A photon leaving Earth right now, traveling at 186,000 miles per second, crosses the distance to the Moon in about 1.3 seconds. It reaches Mars in roughly 12 minutes on average. It passes Jupiter in about 43 minutes. It exits the solar system in a matter of hours. That same photon, moving at the absolute maximum speed permitted by the laws of physics, still needs 4 years and 3 months to reach Proxima Centauri. Light, the cosmic speed limit, the fastest messenger the universe allows, takes years to cross the gap to our nearest neighbour. No spacecraft we have ever built comes close to making this journey practical. Voyager 1, the fastest human-made object heading toward the outer boundaries of our solar system, travels at roughly 38,000 miles per hour. It outruns a rifle bullet several times over and could circle the Earth in under 45 minutes. But point Voyager 1 at Proxima Centauri, and the arithmetic turns cruel. At 38,000 miles per hour, the journey takes roughly 75,000 years. Voyager 1 launched in 1977. If it had been aimed at Proxima Centauri from the start, it would arrive around the year 77,000. To put that duration in perspective, 75,000 years ago, Homo sapiens had not yet painted a single cave wall. The entire recorded history of human civilization, every empire, every war, every revolution, every scientific breakthrough, fits inside fewer than 6,000 years. The flight to the nearest star would swallow that history more than 10 times over and still have tens of thousands of years remaining. And Proxima Centauri is the closest. It sits practically on our doorstep by galactic standards. It is the very first rung on the ladder of interstellar distance, and it already takes 4 years for light to climb it. The next interesting targets, stars like Tau Ceti and Epsilon Eridani that astronomers have identified as potentially hosting planetary systems, lie 10 to 12 light-years away, roughly tripling the travel time. TRAPPIST-1, the much-discussed system with 7 rocky planets, 3 of which orbit in the habitable zone, sits nearly 40 light-years from Earth. The centre of our galaxy is 26,000 light-years distant. The Andromeda Galaxy, the nearest major spiral to our own, sits 2.5 million light-years across intergalactic space. At Voyager 1 speeds, reaching Andromeda would require over 40 billion years, roughly 3 times the current age of the universe. The cosmos is structured at scales that mock the idea of travel between star systems, let alone between galaxies. This is the fundamental distance problem. And it is not a problem of engineering, it is a problem of physics itself. The universe enforces a hard ceiling on how fast anything can travel through space, and that ceiling is the speed of light. Light moves at 186,000 miles per second, roughly 670 million miles per hour. Nothing that carries mass can reach this speed. Nothing that carries information can exceed it. This is not a limitation of current technology waiting to be surpassed by future engines. It is woven into the geometry of spacetime itself, established by Albert Einstein's special theory of relativity in 1905 and confirmed by every experiment conducted in the century since. As an object with mass accelerates toward light speed, its energy requirement climbs toward infinity. You would need infinite energy to push even a single atom to the speed of light. The barrier is not practical. It is absolute. This matters because the speed of light is not just a very large number. It is the speed at which causality itself propagates. It is the rate at which cause connects to effect across the universe. When physicists say nothing can travel faster than light, they are not describing a speed record waiting to be broken. They are describing the fundamental tempo of reality. Exceeding it would mean arriving before you left, which sounds like a thought experiment until you realize it would shatter the relationship between cause and effect that makes physics, chemistry, biology, and consciousness possible. Even approaching the speed of light is staggeringly difficult. Accelerating a spacecraft to just 10% of light speed, roughly 67 million miles per hour, would require energy budgets that dwarf the total output of entire nations. At that velocity, Proxima Centauri is still a 42-year journey. Reaching it in a single human lifetime demands speeds closer to 20 or 30% of light speed, and the energy costs at those velocities enter the realm of harnessing significant fractions of a star's output. No propulsion system in existence or serious development can achieve this. The energy required does not scale gently. It follows a relativistic curve that bends upward with increasing violence as velocity climbs, each additional percentage point of light speed costing exponentially more than the one before. Chemical rockets, ion drives, nuclear pulse propulsion, even the most speculative fusion engine concepts proposed by serious engineers, all of them produce velocities measured in single-digit percentages of light speed at absolute best, and most fall far short of even that modest benchmark. They leave the interstellar distance problem fundamentally intact. The galaxy contains 400 billion stars spread across 100,000 light-years of spiral structure. Under the rules of conventional physics, almost all of it is permanently unreachable. This is where most stories about interstellar distance end. They present the numbers, they let the hopelessness settle into your chest, and then they move on. But in 1994, something remarkable happened. A theoretical physicist named Miguel Alcubierre sat down and asked a question that would rearrange the entire conversation. He did not ask how to make a ship go faster. He did not look for a better engine, a more efficient fuel, a smarter trajectory. He asked whether space itself could be persuaded to move. Alcubierre was working at the University of Wales in Cardiff when he published a short paper in the journal Classical and Quantum Gravity. The title was modest: The Warp Drive, Hyperfast Travel Within General Relativity. The implications were anything but modest. He had found a solution to Einstein's field equations, the mathematical backbone of general relativity that described a region of space-time shaped in a very specific and extraordinary way. In front of this region, space would contract, squeezing together like an accordion being compressed. Behind it, space would expand, stretching apart like taffy being pulled. The region itself, a bubble of perfectly flat and undisturbed space-time, would be carried forward by this asymmetric wave of contraction and expansion at any velocity you chose to specify, including velocities far exceeding the speed of light. The ship sitting inside the bubble would not be moving through space at all. Stop and absorb that statement, because it is the single most important idea in this entire story. This is the critical insight, the conceptual leap that separates warp drive from every other propulsion concept ever proposed. inside the bubble, spacetime is flat. The ship is at rest relative to the local geometry. It does not accelerate. It does not experience crushing g-forces. It does not undergo time dilation relative to the bubble interior. The bubble carries the flat region forward, the way a conveyor belt carries a box. The box does not move relative to the belt surface. The belt moves and the box goes along for the ride. Space contracts ahead, space expands behind, and the flat pocket in the middle surfs the distortion from origin to destination without anyone inside experiencing anything unusual. In principle, the passengers could float in zero gravity, sip coffee, and watch the stars shift outside their windows, while the warp bubble carried them across light years of distance in days, hours, or minutes, depending on how aggressively the space-time geometry was shaped. No inertial dampeners needed, no fictional gravity generators. The flatness of the interior space-time provides all of that naturally. A clock inside the bubble ticks at the same rate as a clock back on Earth. A birthday candle burns normally. A glass of water sits level. Everything inside is ordinary. Only the universe outside is doing something extraordinary. The most stunning feature of this concept is that it does not violate Einstein's cosmic speed limit. Not technically. Not even in spirit. Special relativity forbids objects from moving through local space faster than light, but it places no restriction on how fast space itself can move. This is not a theoretical loophole invented by clever mathematicians looking for an escape hatch. It is a feature the universe already uses on the grandest scales. Right now, at this moment, galaxies at the edge of the observable universe are receding from us faster than light, not because they are rocketing through space at superluminal velocities, but because the space between us and them is expanding. The fabric of the cosmos stretches, and it carries those distant galaxies along with it at recession speeds exceeding the speed of light without any local physics being violated. Each galaxy, in its own local patch of space-time, is barely moving at all. The expansion occurs in the intervening space. No energy condition is broken. No particle exceeds light speed in its local frame. The universe has been doing this since shortly after the Big Bang, for nearly 14 billion years. Faster than light recession of distant galaxies is not exotic or controversial. It is a confirmed, measured feature of the cosmos. Every cosmology textbook discusses it. Every astrophysicist accepts it. The precedent exists in nature. Alcubierre seized this precedent and asked the next logical question. If cosmic expansion can carry galaxies apart faster than light without violating relativity, could the same effect be engineered locally and directionally? Could you compress the expansion of space into a controlled compact distortion and ride it like a surfer rides a wave? The answer, according to his calculations, was yes. Alcubierre realized the same principle could be harnessed deliberately. Instead of waiting for cosmic expansion to carry things apart over billions of years, you could engineer a localized distortion, a controlled, compact bubble of contraction and expansion, and use it to transport a patch of flat spacetime from one location to another at whatever effective velocity the geometry demanded. The ship inside never accelerates through local space. It never approaches, reaches, or exceeds the speed of light relative to its own reference frame. The light speed barrier remains intact everywhere locally, but the bubble, riding the distorted geometry, covers the distance between stars in far less time than a photon traveling through undistorted space along the same route. The cultural context makes this discovery even more striking. The concept of warp drive originated in science fiction. Star Trek, more than any other franchise, burned the idea into popular imagination. The show's starships warped space to hop between solar systems in hours or days, making the galaxy feel like a neighborhood. For decades, physicists dismissed this entirely. Warp drive was a plot device, a narrative convenience for television writers who needed Kirk and Spock at a new planet every week, with no grounding in real physics. The very phrase was shorthand for wishful thinking. Alcubierre reversed the entire flow. He started with the fiction and worked backward through the mathematics of general relativity, and what he discovered was that Einstein's equations genuinely permitted the geometry of a warp bubble. This was not a fringe result printed in a marginal journal. Classical and Quantum Gravity is one of the most respected publications in theoretical and mathematical physics. The derivation was clean, the solution was internally consistent, and it sparked a wave of serious theoretical investigation that continues to this day. What followed was 3 decades of refinements, modifications, and extensions that explored the mathematical landscape of warp drive with increasing sophistication. In 1999, physicist Chris van den Broek demonstrated that a seemingly minor modification to the bubble geometry could dramatically reduce the energy requirements. By introducing a microscopic external cross-section for the bubble while keeping the internal volume macroscopically large, he brought the theoretical energy budget down from a quantity exceeding the total mass energy of the visible universe to a figure on the order of a few solar masses. That is still an inconceivable amount of energy by human standards, but it represented a reduction of more than 20 orders of magnitude and established that the energy problem was not fixed at a single horrifying number. The number could move. The question was how far. The energy figure was still absurd by any practical measure. A few solar masses of negative energy is not something you can order from a supplier. Our entire civilization's annual energy consumption is roughly equivalent to the output of the sun over a fraction of a second. Producing the mass energy equivalent of even one sun, let alone several, and producing it in negative form, remains beyond any technology imaginable today. But the mere fact that the number could be moved at all was theoretically significant. It meant the energy requirement was a variable, not a constant, and that clever geometry could push it in the right direction. In 2002, mathematician Jose Notario introduced an alternative warp metric that achieved superluminal transport with zero volume expansion inside the bubble. His approach eliminated the expansion-contraction asymmetry that defined Alcubierre's original design. The Notario warp drive moved space without expanding or compressing it inside the bubble, offering a cleaner mathematical structure and different properties at the bubble wall. Both approaches required exotic matter to function, and both violated the energy conditions that all known forms of matter and energy obey. But the Notario variant provided something valuable. It served as a second independent proof that the warp concept was not a one-trick artifact of Alcubierre's specific mathematical assumptions. The possibility of warp-like spacetime distortion was not confined to a single clever metric. It was a general feature of what Einstein's equations allowed. Multiple valid roads, built on different mathematical foundations, led to the same category of spacetime geometry. The warp idea had depth, breadth, and resilience. It could be reformulated, optimized, and analyzed from multiple angles. That made it interesting. It also made the barriers it faced more significant, because if multiple formulations all crashed into the same obstacles, those obstacles were probably fundamental. Then came Harold White, and the moment warp drive crossed from theoretical journals into public headlines. In 2011, this NASA aerospace engineer published an analysis suggesting that reshaping the bubble geometry from a thin, flat ring into a thicker, more rounded torus could reduce energy requirements even further, potentially bringing them down to a mass energy equivalent comparable to the Voyager 1 spacecraft rather than a planet or a star. White made international news by setting up an experiment at NASA's Johnson Space Center using a modified device called a White-Jude warp field interferometer to search for microscopic space-time distortions that might indicate embryonic warp field effects. The experiment ultimately did not produce confirmed positive results. Other physicists challenged White's energy estimates, arguing that his optimizations relied on unverified assumptions about the bubble wall thickness and the behavior of the warp geometry at its boundaries. But the cultural impact was already irreversible. News outlets around the world ran stories with headlines suggesting that NASA was building a warp drive. The nuance, that White was merely testing whether an extremely small space-time distortion could be detected using laser interferometry in a controlled laboratory environment, disappeared almost immediately. What people heard was that a NASA scientist was working on faster-than-light travel, and the idea exploded into public consciousness with a force that no correction or caveat could contain. For the first time, a NASA-affiliated researcher was openly investigating warp drive in a laboratory setting. The concept had migrated from the blackboard to the bench, and even though the experimental results remained inconclusive, the psychological barrier had been permanently lowered. Warp drive was no longer just a physicist's thought experiment, it was a research program. Through the 2020s, the pace of theoretical exploration intensified. In 2021, 3 separate research efforts pushed the boundaries of what warp drive mathematics could describe. Alexei Bobrik and Gianni Martire published a general framework for classifying what they called physical warp drives, arguing that the Alcubierre metric was merely one member of a much larger family of warp spacetimes. They demonstrated that subluminal warp drives, bubbles moving at less than the speed of light, could in principle be constructed using only positive energy density, eliminating the most unsettling requirement of the original design. Eric Lentz proposed a superluminal soliton solution using conventional matter sources in what he termed Einstein-Maxwell plasma theory, claiming the energy conditions could be satisfied even at faster-than-light speeds. And Schoenfeld and Lavinia Heisenberg argued that hidden geometric structures within the curvature of spacetime itself could supply positive energy density for certain classes of observers, offering yet another potential route to superluminal travel without exotic matter. These papers generated enormous excitement. Science headlines declared that warp drive had moved from fantasy to engineering possibility. But the physics community responded with scrutiny that was patient, methodical, and devastating. Jessica Santiago, Sebastian Schuster, and Matt Visser published a sequence of analyses in 2021 and 2022, proving that generic superluminal warp drives constructed through the standard shift vector mathematical framework necessarily violate the null energy condition. This was not a critique of any one specific proposal. It was a mathematical proof applicable to the entire class of superluminal warp metrics. The null energy condition requires that the energy density measured along any light-like path never drops below 0. Violating it means requiring matter or energy with properties never observed in nature at any macroscopic scale. In 2025, Bill Selmaster and co-authors identified specific derivation errors in Lentz's claimed positive energy superluminal solution, showing through direct calculation that the geometry still contained regions of negative energy density. The positive energy superluminal warp drive, as Lentz had described it, did not hold up. Then, in 2024, a team led by Jared Fuchs at the Applied Physics Laboratory produced a genuine breakthrough, but one with a critical qualifier. Their constant velocity subluminal warp drive satisfied all known energy conditions using a stable shell of ordinary matter combined with a carefully tailored shift vector distribution. The mathematics was confirmed. The geometry was not reducible to a trivial coordinate transformation. The warp effect was real, but the qualifier was fatal to the interstellar dream. The word was subluminal. Their bubble moved slower than light. It offered a fascinating gravitational property. Passengers experienced no acceleration despite the bubble's motion through space, but it could not outpace a photon. It could not compress a 4-year journey to Proxima Centauri into 4 months or 4 days. It could not solve the distance problem. It was a warp drive that followed the rules, and the price of following the rules was that it could not do the one thing everyone wanted warp drive to do. The result was significant for theoretical physics. It demonstrated that the concept of shaping space-time into a bubble with a flat, force-free interior is not inherently unphysical. Passengers really could be carried without experiencing acceleration. That is a real and interesting gravitational phenomenon. But as a solution to the interstellar distance problem, it offered nothing. You could ride a subluminal warp bubble to Proxima Centauri, but the trip would still take years at best, decades at worst. The same timeline you would face with any conventional subluminal spacecraft. The warp effect made the ride more comfortable. It did not make the ride shorter, and making the ride shorter was the entire point. The most comprehensive assessment arrived in February 2026. Hamed Barzagar, Thomas Buchert, and Quentin Vigneron published a sweeping classification and critical analysis of the entire warp drive literature. Their paper examined every major warp metric proposed since 1994, organized the proposals into categories based on their mathematical restrictions, and identified misconceptions, unjustified simplifications, and outright errors scattered across multiple published works. They proved several new mathematical no-go results that function as structural barriers. Their central conclusion was measured in tone, but unmistakable in substance. When the principles of general relativity are applied correctly and completely, without the simplifications and shortcuts that many earlier papers had relied on, most existing claims regarding physically viable warp drives must be fundamentally reassessed. The positive energy claims were especially vulnerable. Many of them depended on evaluating energy density only from the perspective of a single class of observer, the Eulerian observer at rest relative to the bubble. When the energy conditions were checked for all possible observers, as the physics requires, the violations reappeared. The gap between a valid space-time solution and a physically realizable machine was not merely wide. It was defended by obstacles woven into the very fabric of what general relativity says about matter, energy, and curvature. This is where the story turns, and this is where most popular accounts of warp drive stop being honest with you. Everything described is true. The Alcubierre metric is a valid solution to Einstein's field equations. General relativity genuinely permits the geometry of a warp bubble. Subsequent refinements have mapped the mathematical landscape of warp spacetimes with real intellectual rigor. Subluminal positive energy solutions appear to exist within the boundaries of known physics. These are legitimate achievements in theoretical physics, and they deserve recognition. But a valid solution to a set of equations is not a machine. General relativity also permits solutions describing closed time-like curves, pathways through space-time that loop backward into their own past. It permits naked singularities, points of infinite curvature visible to the universe without any event horizon to shield them. It permits traversable wormholes, bridges connecting distant regions of space through shortcuts in the geometry. None of these have ever been observed in nature. None of them are believed to be physically achievable. The field equations describe what is mathematically self-consistent within the framework. They do not promise that the universe allows every consistent geometry to be built. This pattern, mathematics permitting geometries that physics refuses to build, is not unique to warp drive. It recurs throughout general relativity. The theory is extraordinarily permissive on paper. It is the universe that enforces discipline, and the discipline it enforces on warp drive is absolute. But every superluminal warp metric ever proposed shares a single devastating feature hidden in its own equations. When physicists examine what kind of matter and energy would be needed to actually produce the geometry, the answer is always the same. The bubble requires something called exotic matter, material with a property so extreme that it has never been confirmed to exist anywhere in the observable universe. Its bulk production may be permanently forbidden by quantum mechanics, and the specific property it demands, a quantity called negative energy density, is not merely difficult to manufacture. It may be a substance the universe structurally refuses to contain. The math works. The physics might not. And the distance between those two statements is not a gap that cleverness alone can close. It is a barrier built from the deepest architecture of energy, matter, and the causal structure of space-time. Every superluminal warp metric, no matter how elegantly formulated, runs headfirst into a demand for something the universe does not appear to provide. The demand is specific, quantifiable, and devastating. It has a name, it has a history, and it has resisted every attempt to satisfy it or circumvent it for more than 30 years. What that demand is, why it arises, and why it may represent not just an engineering obstacle but a permanent structural feature of reality, begins now. Every beautiful theory eventually receives a bill. The Alcubierre warp drive received its bill immediately, printed on the same page as the geometry, written into the same equations that made the concept possible in the first place. And the bill is denominated in a currency that may not exist anywhere in the observable universe. No warehouse stocks it. No reaction produces it. No corner of the cosmos has ever been observed to contain it in the quantities required. The warp drive's most fundamental ingredient might be something the universe permanently decided not to create. To understand why, you need to understand how Einstein's field equations actually work. General relativity describes the relationship between matter and the shape of space-time. Mass and energy tell space-time how to curve. Curved space-time tells mass and energy how to move. These two statements, linked by a set of mathematical relationships called the Einstein field equations, form the backbone of modern gravitational physics. They predict black holes, gravitational waves, the expansion of the universe, and the bending of light around massive objects. Every one of these predictions has been confirmed by observation. The equations are not speculative. They are among the most thoroughly tested structures in all of science. When physicists use these equations in the normal direction, they start with a known distribution of matter and energy. A star, a planet, a cloud of gas, and compute what shape spacetime takes in response. The sun curves spacetime around itself. That curvature is what holds the Earth in orbit. A black hole curves spacetime so drastically that nothing, not even light, can escape from within a certain radius. This is how the equations are designed to be used. You specify the stuff. The equations tell you the shape. Alcubierre used the equations in reverse. He specified the shape first. He wrote down the exact spacetime geometry he wanted, a bubble of flat space, surrounded by a region of contraction ahead and expansion behind, and then asked the equations what kind of matter and energy would be needed to produce it. This is a legitimate mathematical operation. The equations run in both directions, but running them backward does not guarantee that the energy distribution the equations spit out corresponds to anything that actually exists in nature. It is the difference between designing a house and then checking whether the building materials are available versus sketching an impossible structure and discovering that it requires beams made of a substance no one has ever seen. When Alcubierre computed the energy distribution required for his warp bubble, the result was unambiguous. The matter threading through the walls of the bubble had to possess negative energy density. Not low energy density, not zero energy density, negative. The energy content of the warp bubble wall had to be less than the energy content of empty space. Less than nothing. Before going further, a common misconception needs to be cleared away. Exotic matter is not antimatter. Antimatter is real, well understood, and routinely produced in particle accelerators. An anti-electron, called a positron, has the same mass as an ordinary electron but opposite electric charge. When matter and antimatter meet, they annihilate each other and release energy. But the mass of antimatter is positive. A kilogram of antimatter weighs exactly the same as a kilogram of ordinary matter and falls downward in a gravitational field in exactly the same way. Antimatter satisfies every energy condition. It is exotic in the colloquial sense, but perfectly ordinary in the physics sense. The exotic matter required for the warp drive is something fundamentally different. It is matter whose gravitational mass is negative, matter that repels rather than attracts, matter that curves space-time in the opposite direction from every substance ever observed. No particle accelerator has ever produced it. No telescope has ever detected it. No theoretical framework has demonstrated a viable pathway to manufacturing it at macroscopic scales. This requires careful unpacking, because the phrase negative energy density sounds abstract until you understand what it means physically. In everyday experience, energy is always positive or zero. A rock sitting on a table has positive energy. A photon streaming through space has positive energy. Even empty space, the vacuum itself, has a baseline energy, the so-called vacuum energy, or zero-point energy that quantum mechanics says cannot be reduced to zero. Everything we have ever measured, every particle, every field, every force carrier, every system in nature, possesses energy that sits at or above this vacuum floor. Negative energy density means something sits below the floor. It means a region of space containing less energy than the vacuum, less than nothing, less than the quietest, emptiest, most inert state the universe allows. If ordinary matter is money in a bank account, negative energy density is not a zero balance. It is a debt so deep that the bank itself owes money to something more fundamental. The concept is not inherently contradictory. Quantum mechanics permits small, fleeting dips below the vacuum energy under extremely constrained conditions. But the warp drive does not need a small, fleeting dip. It needs a sustained, macroscopic ocean of negative energy threaded through a precisely shaped shell of space-time curvature, maintained for the entire duration of the journey. That is a demand of an entirely different magnitude. This is where the energy conditions enter the picture. The energy conditions are a set of mathematical inequalities that physicists use to distinguish physically reasonable matter from physically unreasonable matter within general relativity. They are not fundamental laws derived from first principles. They are empirical constraints. They summarize what every known form of matter and energy in the universe actually does, and every known form of matter and energy in the universe obeys them. The weakest of these is called the weak energy condition. It states that any observer, regardless of how they move through space-time, must measure a non-negative energy density. In plain language, no matter how you look at it, from any reference frame, moving at any speed, the energy density of matter cannot be negative. this seems like a modest requirement. It simply says that the energy of stuff is always zero or above. Every atom, every photon, every neutrino, every piece of dark matter we have ever inferred, all of it satisfies the weak energy condition without exception. The null energy condition is slightly more restrictive. It states that the energy density measured along any light-like path, any trajectory followed by a photon, must be non-negative. This condition applies specifically to how energy behaves along the paths that light travels through spacetime. It is the condition most directly relevant to faster-than-light travel, because it governs how spacetime curvature interacts with the propagation of light signals. The dominant energy condition is the strongest. It requires that not only must energy density be non-negative, but the flow of energy must also be causal. Energy cannot flow faster than light. This condition encodes the idea that the speed of light is not just a speed limit for objects, but a speed limit for the transfer of energy and information through any physical process. If you could pump energy from one place to another faster than a photon could travel between those two places, you could in principle send messages backward in time. The dominant energy condition says this does not happen. Energy respects causality. Information respects causality. Everything that carries physical influence respects the cosmic speed limit. These three conditions are not arbitrary mathematical restrictions that physicists chose for aesthetic reasons or mathematical convenience. They encode the observed behavior of all known matter and radiation across every energy scale, every temperature, every density that has ever been tested. Every experiment, every observation, every measurement in the history of physics is consistent with these conditions. They form a fence around what the universe considers legitimate physical material, and the warp drive requires material that lives on the wrong side of that fence. The Alcubierre warp drive violates all three of these conditions. This was known from the very first paper. Alcubierre himself acknowledged it. The negative energy density required for the warp bubble wall fails the weak energy condition directly. It fails the null energy condition because the energy measured along photon paths through the bubble wall dips below zero. And it fails the dominant energy condition because the superluminal transport of the bubble interior implies energy flow that exceeds the speed of light. The violations are not subtle or marginal. They are structural. The warp geometry cannot exist without them. For years, some researchers hoped this was a feature of Alcubierre's particular mathematical choices rather than a general property of warp drives. Perhaps a different metric, a different bubble shape, a different arrangement of matter could achieve the same result while respecting the energy conditions. This hope was systematically dismantled. In 2021 and 2022, Jessica Santiago, Sebastian Schuster, and Matt Visser published a sequence of proofs demonstrating that generic superluminal warp drives constructed through the standard shift vector formalism necessarily violate the null energy condition. Their analysis did not target one specific metric. It covered the entire class. Any bubble geometry that moves faster than light, regardless of how cleverly it is shaped or optimized, requires regions of negative energy density. In 1998, physicist Ken Olam had already proved an even broader result. He showed that any spacetime geometry permitting superluminal travel of any kind, not just warp drives, must violate a generalized energy condition called the average null energy condition. The prohibition is not confined to Alcubierre. It extends to traversable wormholes, Krasnikov tubes, and every other theoretical shortcut through spacetime that has ever been proposed. Wherever faster-than-light transport appears in the mathematics of general relativity, negative energy appears with it, like a shadow that cannot be separated from the object casting it. This universality is what makes the energy condition barrier so formidable. It is not a bug in one design. It is a structural feature of how spacetime geometry interacts with the speed of light across all designs. The universe appears to have welded the cosmic speed limit to the energy condition so tightly that breaking one requires breaking the other, and breaking the other requires a substance that the same universe may have permanently refused to supply. Some physicists have pointed out that quantum field theory in curved spacetime does permit small violations of the energy conditions under specific circumstances. The Casimir effect is one example. The Hawking radiation emitted by black holes involves another. In both cases, Quantum effects create temporary or localized regions where negative energy density exists. This has led to speculation that the energy conditions might be relaxable at larger scales under sufficiently exotic circumstances. But every serious analysis of these quantum violations reveals the same pattern. They are small, they are transient, and they are bounded by the quantum inequalities. Nature allows you to dip below the vacuum floor, but it yanks you back before you can establish permanent residence there. The scale of the negative energy required for an Alcubierre bubble is where the problem transitions from theoretically troubling to practically absurd. The first serious energy estimates came from Michael Fenning and Lawrence Ford in 1997. They applied quantum inequality constraints to the warp bubble geometry and calculated that the total negative energy needed to create a bubble large enough to transport a macroscopic object would exceed the total mass energy of the warp. Entire observable universe by 10 orders of magnitude. That number deserves repetition because the human mind tends to slide past it. Not 10% more than the energy content of the observable universe. Not 10 times more. 10 billion times more. The observable universe contains approximately 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. Each star burns with the fury of nuclear fusion, converting millions of tons of hydrogen into energy every second. Add up all of that energy, every photon emitted by every star that has ever burned in every galaxy across 14 billion years of cosmic history, multiply the sum by 10 billion, and convert the entire total into negative form. That was the price tag for a single warp bubble large enough to carry a spacecraft. Subsequent work over the following decades chipped away at this figure, but the reductions were always measured relative to the original absurdity, and even the most aggressive optimizations left the requirement far beyond any conceivable technology. Chris van den Broek showed in 1999 that clever geometric modifications could reduce the requirement to a few solar masses of negative energy. Our Sun contains roughly 2 times 10 to the 30 kilograms of mass. Converting all of that to energy via Einstein's equivalence yields a number beyond human intuition. Yet van den Broek's geometry required several times that amount in negative form. Harold White argued in 2011 that further optimization of the bubble shape might bring it to roughly the mass energy of a planet like Jupiter. Some later calculations have claimed reductions even further, down to the mass energy of a large spacecraft. Though these estimates rest on assumptions about bubble wall thickness and geometry that have not been independently verified, and that the 2026 Barzagar, Buchert, and Vigneron review questioned on fundamental mathematical grounds. Even accepting the most optimistic estimate, the problem remains devastating. Jupiter has a mass of approximately 1.9 times 10 to the 27 kilograms. Converting that mass entirely into energy via Einstein's famous equivalence yields a number so large that it exceeds the total energy output of our Sun over its entire 10 billion year lifetime by a comfortable margin. And you need that energy in negative form. Not positive energy converted or redirected or concentrated. Negative energy. Energy below the vacuum. A substance that no laboratory on Earth has ever produced in quantities larger than the fleeting quantum fluctuations between 2 metal plates separated by nanometers. Those metal plates are the Casimir effect, and they represent the only confirmed instance of negative energy density ever measured in a laboratory. The effect was predicted by Dutch physicist Hendrik Casimir in 1948 and confirmed experimentally decades later with increasing precision. The setup is elegantly simple in principle and fiendishly difficult in practice. When 2 uncharged, perfectly flat, conducting metal plates are placed extremely close together in a vacuum, typically separated by distances measured in hundreds of nanometers, the quantum vacuum between them has slightly less energy than the vacuum outside. This happens because the narrow gap restricts which quantum fluctuations can exist between the plates. In open space, virtual particles of all wavelengths constantly pop in and out of existence, borrowing energy from the vacuum for fleeting instants before returning it. Between the plates, only fluctuations whose wavelengths fit within the gap can exist. Longer wavelengths are excluded. The result is that the vacuum between the plates contains fewer fluctuations than the vacuum outside, giving it a lower energy density. That lower density is measurably below the vacuum baseline. It is, in the precise technical sense, negative. The effect is real. The attractive force between the plates has been measured to within a few % of theoretical predictions. It is a triumph of quantum electrodynamics, confirming that the vacuum is not truly empty, but seethes with activity that can be manipulated under very specific conditions. But confirming the prediction took nearly half a century of painstaking experimental effort. Casimir published his theoretical argument in 1948, and the physics community accepted the mathematics almost immediately. Actually measuring the effect was another matter entirely. It required metal surfaces polished to near atomic smoothness, positioned with nanometer precision, isolated from thermal noise, mechanical vibration, and electrostatic contamination. It was not until 1997 that physicist Steve Lamoureux at the University of Washington achieved the first high-precision confirmation, using a gold-coated sphere and a flat plate separated by distances smaller than the width of a human red blood cell. The force he measured was minute, roughly equivalent to the weight of a short strand of human hair resting on a surface. That is the scale at which negative energy density has been experimentally verified. The warp drive demands it at a scale that is roughly 100 trillion times larger. The Casimir effect proves that negative energy density is not forbidden by physics in absolute terms. Quantum mechanics does allow small localized dips below the vacuum floor, but the distance between the Casimir effect and the warp drive is not a gap. It is a chasm that spans dozens of orders of magnitude. The Casimir effect produces negative energy densities on the scale of nanometers, between plates that are almost touching. The warp drive requires negative energy densities sustained across meters or kilometers of bubble wall, maintained continuously for the duration of an interstellar journey that could last hours, days, or years depending on the effective velocity. The Casimir effect is a whisper. The warp drive needs a sustained roar louder than every sound ever produced in the history of the universe combined, and it needs that roar to be made of silence, of less than nothing, of energy below the floor. Quantum mechanics does not merely fail to provide what the warp drive needs, it appears to actively forbid it. The quantum inequalities derived by Lawrence Ford and Thomas Roman across a series of papers beginning in the mid-1990s establish a fundamental trade-off between the magnitude of negative energy and the duration for which it can exist. Think of it as a conservation law for impossibility. The universe allows brief flickers of negative energy at the quantum scale, the kind produced by the Casimir effect, but it enforces a strict budget. The more negative energy you concentrate in a region, the shorter the time that concentration can be sustained before quantum effects force it back to zero or above. A large burst of negative energy can exist for an extraordinarily brief instant, far shorter than the time it takes light to cross an atomic nucleus. A smaller trickle of negative energy can persist for a somewhat longer period, but still far too briefly for any macroscopic engineering purpose. The product of the magnitude and the duration is bounded from above. You cannot cheat this budget. You cannot borrow from one region to pay another. The constraint is local and absolute. A concrete example makes the trade-off visceral. The Ford-Roman inequalities imply that a pulse of negative energy comparable in magnitude to even the most optimistic warp drive estimates could persist for a duration so vanishingly brief that light would barely have time to cross a single atom before the quantum budget forced the energy back above zero. That is the timescale the universe permits. The warp drive needs that same magnitude sustained not for atomic crossing durations but for hours, days, or weeks of continuous operation across a shell meters thick. The gap between what quantum mechanics briefly tolerates and what the warp drive continuously demands is not a few orders of magnitude. It is dozens upon dozens, a mismatch so severe that no known physical principle bridges it. This budget is devastating for the warp drive. The bubble geometry requires a specific negative energy density distributed through a shell of finite thickness. That shell must maintain its structure for the entire transit. A journey from Earth to Proxima Centauri, even at superluminal speeds, requires the bubble to persist for at least the subjective duration of the trip, which might be hours or days depending on the geometry and effective velocity. The quantum inequalities say this combination of magnitude, spatial extent, and duration cannot be simultaneously achieved. You can have enough negative energy, but not for long enough. You can have it for long enough, but not in sufficient quantity. Poor. The trade-off is enforced at the quantum level, and no known mechanism circumvents it. Some physicists have explored whether quantum field theory in curved spacetime might relax these constraints in ways that could help the warp drive. The quantum inequalities were originally derived in flat Minkowski spacetime, and there is legitimate ongoing debate about whether they take exactly the same form in the highly curved geometry of a warp bubble wall, where spacetime is being bent, twisted, and compressed by the very distortion the bubble requires. Some analyses suggest that spacetime curvature can modify the detailed shape of the inequalities, altering the precise constants in the trade-off formula. But even the most optimistic of these analyses concludes that curvature effects modify the inequalities without eliminating them. The fundamental trade-off between magnitude and duration persists regardless of the background geometry. Others have investigated whether semi-classical gravity, the theoretical framework that combines quantum field theory with classical general relativity and represents our best current tool for analyzing quantum effects in curved spacetime, might reveal loopholes or exceptions that could be exploited. So far, no such loophole has been confirmed by independent analysis. The constraints appear robust across every framework in which they have been tested. This is the wall that the warp drive hits, not a technological wall that future engineering might breach, not a funding wall that a sufficiently motivated civilization could overcome. A wall built into the joint structure of quantum mechanics and general relativity, the two deepest and most successful theories in the history of physics, acting in apparent concert. The warp geometry is permitted by classical general relativity running in reverse. The energy distribution required to produce that geometry is constrained and potentially forbidden by quantum mechanics running forward. The two pillars of modern physics, the theory of the very large and the theory of the very small, appear to conspire against the warp drive from opposite directions. General relativity says the shape is fine. Quantum mechanics says the ingredients to build that shape cannot exist in the required form, at the required magnitude, for the required duration. The result is a theoretical object trapped between two frameworks, mathematically consistent within one and physically prohibited within the other. It is an idea that lives on paper and dies in reality. The situation for subluminal warp drives is different but not redemptive. As the Fuchs team demonstrated in 2024, and as Bobrick and Martier argued in their 2021 framework, subluminal warp bubbles constructed with positive energy and ordinary matter may be physically possible. The energy conditions can potentially be satisfied. The quantum inequality constraints do not apply in the same way, because the bubble is not exceeding light speed and does not generate the same horizon and curvature pathologies. These are genuine, peer-reviewed results that advance our understanding of how space-time geometry can be shaped by realistic matter distributions. But subluminal means slower than light. A subluminal warp bubble cannot outrun a photon. It cannot compress a 4-year journey into 4 days. It cannot bridge the gap to even the nearest star in a time frame that would make human interstellar exploration feasible. If you travel from Earth to Proxima Centauri inside a subluminal warp bubble, the trip still takes more than 4 years, assuming you approach but never reach the speed of light. The warp effect gives you a perfectly flat interior where you experience no acceleration and no tidal forces, which is a remarkable gravitational phenomenon and a legitimate result in the physics of space-time curvature. But it does not shorten the journey. The universe has offered a compromise. You can have a warp bubble or you can have faster than light travel. You cannot have both. The version that follows the rules cannot break the barrier. The version that breaks the barrier cannot follow the rules. This creates a divide that runs through the entire field of warp drive research, like a geological fault line. On one side stand the physically realizable subluminal constructions that respect the energy conditions, but offer no improvement over conventional travel times between stars. They are scientifically interesting. They demonstrate that space-time can be shaped in unexpected ways by ordinary matter. They may eventually find applications in gravitational physics or in propulsion concepts that have nothing to do with interstellar travel. But they do not solve the distance problem. They do not bring the stars closer. On the other side stand the superluminal constructions that would actually make interstellar travel practical. The warp drives that compress years into days and make the galaxy navigable on human timescales. But these require exotic matter that has never been observed and that quantum mechanics appears to structurally forbid at the necessary magnitudes and durations. Every attempt to cross this divide has failed. Every proposed bridge has either been shown to contain hidden regions of negative energy upon closer inspection, or has turned out to be subluminal when the mathematics was checked thoroughly, or has been built on derivation errors identified and corrected by subsequent peer review. The divide is not a temporary embarrassment that cleverer mathematics will dissolve. It is not a puzzle waiting for the right genius to solve. It appears to be a structural feature of how general relativity and quantum field theory interact at the boundary between subluminal and superluminal motion. The energy problem alone would be enough to render the warp drive a theoretical curiosity rather than a plausible technology. But the energy problem is not alone. It is the first obstacle in a cascade that grows worse with each step. Assume, for the sake of argument, that some future civilization discovers a way to generate macroscopic quantities of negative energy. Assume they solve the quantum inequality problem and find a mechanism to sustain the required energy density for the duration of an interstellar journey. Assume the exotic matter is produced, shaped and threaded into the warp bubble wall with precision that no known technology could approach. Grant all of this. Hand the warp drive its impossible fuel and let it ignite. What happens next is worse, because the moment the bubble exceeds the speed of light, 3 new catastrophes erupt simultaneously, and each one is independently fatal to the dream of using warp drive as a practical interstellar transport. The crew loses all ability to control, steer, or stop the bubble. They become passengers on a runaway geometry with no steering wheel and no brakes, sealed inside a pocket of space-time that cannot communicate with its own walls. The existence of a faster-than-light vehicle shatters the causal structure of the universe itself, opening doorways to genuine backward time travel and logical paradoxes that threaten the self-consistency of physics. And the destination, the planet or star system the travelers were trying to reach, faces annihilation from a concentrated burst of lethal radiation released by the bubble the instant it decelerates. The impossible fuel was only the entrance fee. What lies beyond the door is a structure built on collapsing floors, and every floor gives way beneath you. Assume the impossible. Assume that some civilization, millions of years more advanced than anything humanity might become, discovers how to produce macroscopic quantities of negative energy. Assume they solve the quantum inequality problem that caps the magnitude and duration of below-vacuum energy states, finding a mechanism that nature somehow left unlocked. Assume they can shape exotic matter with subatomic precision and thread it through the walls of a warp bubble in exactly the configuration the Alcubierre metric demands, maintaining it with perfect stability against perturbations that would ordinarily cause instant collapse. Grant every impossible thing the previous argument said cannot be granted. Erase the energy barrier entirely. Hand the warp drive its fuel that does not exist and may never exist, and let the bubble form around the ship. Let the geometry of space-time begin to contract ahead and expand behind. Let the bubble accelerate past the speed of light. What happens next does not save the travelers, it condemns them. Because the moment the warp bubble crosses the threshold from subluminal to superluminal velocity, a cascade of new catastrophes erupts from the physics of the bubble itself, and each one is independently fatal to the idea that warp drive could ever function as a practical vehicle for reaching the stars. The first catastrophe is the horizon. In 2002, mathematician José Notario published an analysis that exposed a problem buried in the geometry of every superluminal warp metric. When a warp bubble exceeds the speed of light, an event horizon forms at its front wall. This is not a metaphor. It is the same type of causal boundary that surrounds a black hole, a surface beyond which signals cannot propagate in one direction. Inside a black hole, nothing can escape outward past the event horizon. Inside a superluminal warp bubble, nothing can escape forward past the bubble wall. The reason is identical in both cases. The geometry of space-time prevents light from crossing the boundary. Here is why. Inside the warp bubble, space-time is flat. Light travels at its normal speed within this flat pocket, 186,000 miles per second relative to the local geometry. But the bubble itself is moving faster than light relative to the space outside. This means that a photon launched from inside the bubble toward the front wall is trying to chase a surface that recedes faster than the photon can travel. The light never catches the wall. It falls behind. perpetually unable to reach the boundary. From the perspective of the crew inside, the front wall of their own bubble has become unreachable. They can see it, they know it exists, but no signal they send, no laser pulse, no radio transmission, no physical object they eject from the ship can ever reach it. This transforms the warp bubble from a vehicle into a sealed container. The crew cannot communicate with the front of the bubble. They cannot send instructions to the mechanism that maintains the warp geometry ahead of the ship. They cannot adjust the contraction rate of space in front of them. They cannot steer. They cannot change course. They cannot slow down. They cannot stop. Every control surface that matters, every part of the bubble geometry that determines where the ship goes and how fast it gets there, sits on the other side of an event horizon that the crew can never cross. They are passengers sealed inside a runaway geometry with no steering wheel, no throttle, and no brakes. Think of a submarine plunging through the deep ocean at a speed so extreme that the water rushing past its hull has torn away the rudder, flooded the control room, and sealed every hatch that connects the crew to the exterior. The submarine continues on its trajectory, but the people inside have lost all ability to influence where it goes. The vessel is no longer a vehicle, it is a projectile. That is what a superluminal warp bubble becomes the instant it crosses the light speed barrier. The crew can sit inside their perfectly flat, perfectly calm pocket of space-time, experiencing no acceleration and no discomfort, while having absolutely zero influence over where the bubble carries them, whether it stops or what happens when it arrives. The warp drive provides a smooth ride to a destination the passengers cannot choose, and a fate they cannot alter. This leads directly to the second catastrophe, the control paradox. Even if the horizon problem could somehow be circumvented, perhaps through some yet undiscovered modification to the metric that restores causal contact between the interior and the bubble wall, a more fundamental question remains. How do you create the warp geometry in the first place? The Alcubierre bubble requires spacetime to be contracted ahead of the ship and expanded behind it. But ahead of the ship is precisely the region of space the ship has not yet reached. To warp the space in front of you, you need to manipulate spacetime at your destination before you arrive there. You need the exotic matter already arranged at the far end of the journey before the bubble sets out. This is a bootstrapping problem. The warp drive requires something to already exist at the end point in order for the journey to begin. One proposed solution is to set up the warp geometry along the entire route before departure. Some external agent, perhaps a network of pre-positioned exotic matter generators stretching from origin to destination across every light year of the route, would sculpt the space-time corridor in advance, shaping the contraction and expansion profiles along a fixed path like laying railroad tracks across a continent before the locomotive departs. The bubble would then ride these pre-built tracks to its endpoint. The destination, the velocity profile, the deceleration point, all of it would be fixed before launch. The passengers would be cargo on a rail line, someone else constructed. But this proposal vaporizes the entire advantage of warp drive. The point of a warp drive is that it allows you to travel somewhere new, somewhere unexplored, somewhere you have never been. If you must first send conventional speed equipment to the destination to set up the space-time geometry, you have not bypassed the speed of light barrier, you have merely deferred it. The equipment travels at subluminal speeds. The setup takes years, decades, or centuries depending on distance. The warp bubble then rides the pre-built corridor, arriving quickly but only after the slow, conventional preparation has been completed. This is not faster than light travel. It is faster than light travel that requires slower than light infrastructure, and the infrastructure faces exactly the same distance problem that warp drive was supposed to solve. Consider what corridor construction actually involves. You would need to survey the route in advance, mapping every gravitational anomaly, every dense molecular cloud, every rogue planet or stellar remnant that could disrupt the carefully shaped geometry along the path. You would need to transport exotic matter generators to positions along the route, spacing them at intervals dictated by the curvature profile the bubble requires, across light years of empty, uncharted space. Each generator would need to arrive, deploy, calibrate relative to its neighbours, and begin shaping space-time with extraordinary precision. The generators would need to communicate to maintain geometric coherence along the corridor, but that communication would travel at light speed at best, Coordination across a multi-light-year corridor would involve years of signal delay between adjacent stations. Any disruption along the route, a passing star whose gravity warps the corridor geometry, a dense interstellar cloud drifting across the path, a gravitational wave from a distant binary merger that subtly distorts the local curvature, could throw the entire profile out of alignment and require recalibration that takes additional years to propagate from station to station. The infrastructure is not a highway. It is a precision instrument spanning interstellar distances, maintained in a medium that is never perfectly still, and assembled by equipment that must crawl to its deployment site at speeds far below light. A corridor to Proxima Centauri would take decades to construct at minimum, using propulsion systems that do not yet exist, carrying exotic matter that has never been produced. A corridor to a star 40 light-years away would require centuries of preparation. The warp bubble at the end of this vast generational investment saves time only relative to the corridor it rides, not relative to the civilization that spent generations laying the track. The alternative is even worse. If no pre-existing corridor is laid, the bubble must somehow generate the required space-time distortion ahead of itself as it moves. But we have already established that the crew inside cannot send signals forward past the horizon. So who or what controls the geometry in front of the bubble? Nothing inside the bubble can do it. Nothing outside the bubble knows the bubble is coming until it has already passed, because the bubble outruns its own light. The geometry at the front must either be pre-arranged or spontaneously self-generating, and no known mechanism in physics produces the required exotic matter configuration spontaneously. The warp bubble needs a pilot who sits outside the vehicle, outside the event horizon, and outside the causal reach of everyone aboard. The machine requires a controller who cannot be inside it, and a passenger who cannot control it. The concept eats its own functionality. It requires a controller who cannot be aboard and passengers who cannot control their own journey. The third catastrophe cuts deeper than engineering. It cuts into the fabric of causality itself. In special relativity, the speed of light is not merely a speed limit. It is the boundary between cause and effect. Events separated by distances that light can bridge in the available time are called time-like separated, and they can have a causal relationship. One can cause the other. Events separated by distances too large for light to bridge are called space-like separated, and they cannot influence each other. No signal, no force, no interaction can connect them. This boundary is what preserves the logical ordering of the universe. Causes precede effects. Messages arrive after they are sent. The past determines the future, not the other way around. Faster than light travel breaks this boundary, and breaking this boundary does not merely allow you to arrive somewhere quickly, it allows you to arrive before you left. This is not hyperbole. It is not a dramatic exaggeration chosen for narrative effect. It is a direct mathematical consequence of special relativity, combined with the principle that the laws of physics look the same in all inertial reference frames, a principle called Lorentz invariance. If you can send a signal or a ship faster than light in one reference frame, then an observer in a different reference frame, one moving at ordinary subluminal speed relative to the first, will see that signal or that ship arrive at its destination before it departed from its origin. The ordering of events reverses. The effect precedes the cause. This is the tachyonic anti-telephone argument, first articulated in the context of hypothetical faster-than-light particles and extended to warp drives by Alan Everett in 1996. The argument works as follows, and every step is a consequence of physics that has been confirmed by experiment. Observer A sits on Earth. Observer B travels past Earth at high ordinary speed, say 50% of the speed of light, heading toward a distant star. Both observers have access to warp drives. Observer A sends a warp-driven ship from Earth to the distant star. The ship arrives before light from Earth could reach that star, because the warp bubble carries it superluminally. Observer B, in their fast-moving reference frame, witnesses something different. Due to the Lorentz transformation that mixes space and time coordinates between reference frames, Observer B sees the arrival of the ship at the distant star as happening before the departure from Earth. The temporal ordering has been reversed. Events that were cause and effect in one frame are effect and cause in another. Now Observer B sends a return ship back toward Earth using their own warp drive, launching it from their reference frame in what they consider to be the normal forward direction of time. But from Observer A's reference frame, this return journey also undergoes a Lorentz transformation. The result is that the return ship arrives at Earth before the original ship departed. A message has travelled backward in time. Information from the future has reached the past. The causal structure of the universe has been broken, and the break was accomplished using nothing more exotic than 2 warp drives and the well-established physics of Lorentz invariance. In 2023, physicists Baruch Shoshani and Ben Snodgrass demonstrated this rigorously within general relativity. They generalized the standard warp drive metric to allow switching between reference frames through a modified lapse function, and showed that 2 warp drives could be combined to construct a closed time-like geodesic, a path through spacetime that loops back to its own starting point in both space and time. A test particle following this path would return to its own past. This was not a flat space thought experiment. It was a full general relativistic construction, using curved spacetime and warp geometries, producing a time machine. The implications are staggering and extend far beyond the warp drive itself. If a functioning superluminal warp drive can be built, then a time machine can also be built using the same technology and the same physics. This connection is not a side effect that might be engineered away with a clever modification. It is not a minor technical complication that a sufficiently advanced civilization could work around. It is an inescapable mathematical consequence of combining faster-than-light motion with the Lorentz invariance of physical law, a symmetry principle that has been confirmed by every experiment in the history of particle physics. Every superluminal warp drive is, in principle, a component of a time machine. You cannot have one without enabling the other. The warp drive does not just move you through space, it gives you the tools to dismantle the ordering of time. The universe may have an opinion about this. In 1992, Stephen Hawking proposed what he called the chronology protection conjecture. Hawking suspected that the laws of physics conspire to prevent the formation of closed time-like curves, not through any single mechanism, but through a convergence of quantum effects that destabilize any space-time geometry approaching the threshold of time machine formation. He suggested that quantum vacuum fluctuations would grow without bound as a closed time-like curve began to form, generating infinite energy densities that would destroy the time machine before it could function. The conjecture remains unproven. No rigorous theorem establishes that chronology protection holds in all cases, but neither has anyone demonstrated a stable, physically realizable closed time-like curve that survives quantum scrutiny. If Hawking was right, and a growing number of theoretical calculations support at least the spirit of his conjecture, the implications for warp drive are devastating. The chronology protection conjecture does not merely forbid time machines, it forbids any technology that would enable the construction of a time machine. Since a superluminal warp drive enables time machine construction as a matter of mathematical necessity, chronology protection would forbid the warp drive itself. The universe would not wait for someone to assemble a time machine from warp components. It would prevent the warp components from functioning in the first place. The same quantum effects that destroy a nascent time machine would destabilize a superluminal warp bubble before it could form, because the bubble is already latently a time machine component. This is speculative. Chronology protection has not been proven, but it represents the most conservative interpretation of what known physics implies about faster-than-light travel. The universe may tolerate many strange things: black holes, neutron stars, cosmic inflation, the quantum vacuum, but it may draw an absolute line at time travel, and that line would cut directly through the heart of every superluminal warp drive ever proposed. The fourth catastrophe comes from the quantum vacuum itself, and it attacks the warp bubble from within. In 2009, physicists Carlos Barcelo, Stefano Finazzi, and Stefano Liberati published an analysis applying quantum field theory to the Alcubierre warp drive spacetime. Their results were alarming. They showed that when a warp bubble exceeds the speed of light, the geometry of the bubble wall develops properties analogous to those of a black hole event horizon. Specifically, the curved spacetime at the bubble boundary generates Hawking radiation. The same quantum thermal emission that Stephen Hawking predicted would be produced by black holes in 1974. Black hole Hawking radiation is ordinarily feeble, so faint that it has never been directly detected despite decades of searching. For a stellar mass black hole, the temperature of the Hawking radiation is a tiny fraction of a degree above absolute zero, far too cold and far too dim for any current instrument to measure. The radiation exists in theory and is broadly accepted by the physics community, but its practical effects on stellar mass black holes are negligible over the current age of the universe. However, the temperature of Hawking radiation scales inversely with the size of the horizon that produces it. Smaller horizons produce dramatically hotter radiation. A black hole the mass of a mountain would glow white hot with Hawking emission. A black hole the mass of a large naval vessel would radiate at temperatures exceeding those inside stellar cores. The bubble wall of a warp drive is far smaller than a black hole event horizon, and the geometry is far more extreme. When Barcelo, Finazzi, and Liberati calculated the temperature of the Hawking radiation generated by a superluminal Alcubierre bubble, the result was catastrophic. The temperature inside the bubble wall region would soar to approximately 10 to the 32nd power Kelvin. That number is almost meaningless in human terms, so let these comparisons anchor it. The core of our sun burns at approximately 15 million Kelvin. That is hot enough to fuse hydrogen into helium, powering the star that keeps Earth alive. The core of the most massive stars, blue supergiants nearing the end of their lives, burns at roughly 3 billion Kelvin, hot enough to fuse silicon into iron. The temperature of the universe during the first fraction of a second after the Big Bang, during the era when the fundamental forces of nature were still separating from a unified state, reached approximately 10 to the 32nd power Kelvin. The Hawking radiation generated by a superluminal warp bubble would reproduce those primordial thermal conditions, the most extreme temperatures the universe has ever contained, inside the walls of the bubble. Everything inside the bubble would be incinerated. The exotic matter maintaining the bubble geometry would be disrupted and destroyed. The bubble itself would become unstable and collapse. The warp drive would not merely fail, it would fail by converting its own interior into a furnace hotter than any naturally occurring environment in the modern universe. The destruction would unfold through a runaway feedback loop with no stable endpoint. The Hawking radiation generated at the bubble wall carries energy, and that energy must come from somewhere. In the warp drive geometry, it drains from the exotic matter sustaining the bubble structure. As the exotic matter degrades, the bubble geometry destabilizes. A destabilizing geometry produces sharper curvature gradients at the bubble wall, which in turn generate even more intense Hawking radiation. The intensified radiation erodes the exotic matter faster. The eroding matter produces sharper gradients still. The process feeds on itself, a thermal runaway in which the bubble's own quantum emissions systematically dismantle the structure, holding it together. Barcelo, Finazzi, and Liberati described this as a fundamental semi-classical instability, not a malfunction that better engineering or additional exotic matter could prevent, but an intrinsic feature of how quantum fields respond to the specific spacetime curvature that a superluminal warp bubble necessarily creates. The bubble does not merely overheat, it devours its own foundation, each quantum of radiation pulling another brick from the wall until the entire geometry collapses. The researchers noted that these problems vanish entirely at subluminal speeds. When the bubble moves slower than light, no event horizon forms at the bubble wall, no Hawking radiation is generated, and the interior remains at ambient temperature. This reinforces the pattern that emerged earlier. Subluminal warp drives avoid the catastrophic physics. Superluminal warp drives trigger it. The speed of light is not just a barrier, it is a tripwire. Cross it, and the physics of the bubble turns hostile. Stay below it, and the bubble works but cannot solve the interstellar distance problem. Every escape route leads back to the same locked door. The fifth catastrophe waits at the destination, and it may be the cruelest of all, because it punishes not the travellers but the people they came to find. In 2012, physicists Brendan McMonigal, Geraint Lewis, and Philip O'Byrne published a study examining what happens to particles encountered by a warp bubble during its journey through interstellar space. The interstellar medium, the thin gas and dust that fills the space between stars, is often described as a vacuum, and by everyday standards it is. But it is not empty. It contains a scattering of hydrogen atoms, lone protons stripped of their electrons, stray cosmic ray particles accelerated to near-light speeds by distant supernovae, and active galactic nuclei, photons from starlight and the cosmic microwave background, and traces of interstellar dust grains composed of silicates and carbon compounds. The density is extraordinarily low, roughly 1 atom per cubic centimetre in typical regions of the galactic disk, dropping to even lower densities in the spaces between spiral arms. But a warp bubble travelling at superluminal speeds sweeps through enormous volumes of this material, and even a thin medium adds up when you are crossing light years of distance. As the bubble moves, particles from the interstellar medium interact with the extreme spacetime curvature of the bubble wall. Some particles are deflected, others are captured. The captured particles become trapped in the geometry of the bubble wall, unable to escape forward or backward, carried along with the bubble as it crosses light years of space. Over the course of an interstellar journey, the bubble accumulates a growing shell of trapped particles, each one compressed and blue-shifted by the intense curvature at the bubble boundary. The longer the journey, the more particles accumulate. The greater the distance travelled, the higher the energy concentrated in this growing shell. When the bubble decelerates, the geometry that was trapping these particles unravels. The trapped particles are released in a concentrated burst, focused primarily in the forward direction, directly at the destination. McMoneagle and his colleagues calculated that this burst would consist of extremely high-energy gamma rays and relativistic particles, blue-shifted to energies far exceeding anything produced by natural astrophysical processes. The energy of the burst depends on the distance travelled and the density of the interstellar medium along the route. For a journey of even a few light years through typical interstellar space, the released energy would be sufficient to destroy anything at the destination, any space station, any planet, any biosphere. For longer journeys spanning dozens or hundreds of light years, the energy scales upward without any known upper limit. The physics does not cap the accumulated energy. The bubble simply keeps collecting particles as long as it travels, and it dumps all of them at once when it stops. The researchers stated their conclusion directly. Any people at the destination would be blasted into oblivion by gamma rays and high-energy particles focused by the extreme blue shifts in the forward region of the decelerating bubble. The warp drive does not arrive. It detonates. The vehicle designed to carry explorers to new worlds would annihilate those worlds upon arrival. The longer the journey, the more devastating the explosion. A trip across the galaxy would release more energy at the destination than a supernova. One might suggest aiming the bubble slightly off target and decelerating to the side of the destination rather than directly at it. McMoneagle's analysis addressed this. The particle release is not perfectly collimated. High-energy particles scatter in multiple directions as the bubble geometry unravels. Even an offset approach would deliver catastrophic radiation to a wide area surrounding the destination. The arrival footprint of a warp bubble is not a pinpoint. It is a zone of destruction whose radius depends on the journey distance and the accumulated particle energy. There is no safe arrival vector. There is no gentle deceleration. The physics of the bubble makes every arrival an act of violence against the destination. This creates a paradox that would be darkly comic if it were not so devastating to the dream of interstellar travel. The warp drive was conceived as a way to visit other star systems, to explore exoplanets, to make contact with whatever might exist out there. Instead, it functions as a weapon of mass destruction aimed at the very places the travelers want to reach. You cannot explore what you have annihilated. You cannot make peaceful contact with the civilization you have just sterilized. The faster you travel and the farther you go, the more destructive your arrival becomes. The warp drive does not bring the stars within reach. It makes reaching the stars an act of annihilation. Step back now and look at what the warp drive actually requires, not as a fantasy, but as a physical system evaluated against the known laws of the universe. It requires exotic matter that has never been observed, and that quantum mechanics may permanently forbid. It requires energy densities that exceed the output of stars, compressed into negative form. It creates an event horizon that seals the crew away from every control surface on their own vehicle. It demands pre-built space-time corridors that themselves require subluminal infrastructure, eliminating the speed advantage. It enables the construction of time machines, which the universe may structurally prohibit through chronology protection. It generates Hawking radiation at temperatures matching the Big Bang, incinerating everything inside the bubble wall. And it annihilates the destination upon arrival through a focused particle burst whose energy has no upper bound. These are not 5 versions of the same problem wearing different masks. They are 5 independent physical mechanisms, each arising from a different branch of physics, each attacking a different aspect of the warp drive concept, and each one individually sufficient to render the technology unworkable as a means of reaching the stars. The energy problem comes from quantum mechanics. The horizon problem comes from the geometry of superluminal spacetime. The control problem comes from causal structure. The causality problem comes from Lorentz invariance and general relativity. The arrival problem comes from the interaction between the bubble geometry and the interstellar medium. They share no common fix. Solving one does not touch the others, and no proposed modification to the warp metric has ever simultaneously addressed all 5. The warp drive began this story as the most elegant theoretical escape ever imagined from the prison of interstellar distance. It ends here as something very different. Not a broken tool that needs better engineering. Not a promising prototype that needs more funding or a few more decades of development. But a concept that reveals, through its own cascading internal failures, the depth, interconnectedness, and apparent permanence of the rules that govern space-time, energy, causality, and the propagation of information across the cosmos. Those rules are not arbitrary obstacles placed in our path by an indifferent universe. They are the architecture of the universe itself. They are what makes stars burn, planets form, chemistry work, and conscious beings possible. And now we confront what it means that even our most powerful theoretical imagination, operating entirely within the framework of our best confirmed physical theories, runs into walls that appear to be not merely difficult but fundamental, structural, and woven into the deepest fabric of reality itself. We have spent this entire journey watching the most elegant theoretical escape in the history of physics collapse under its own weight. The Alcubierre warp drive begins as a beautiful idea, a geometry of space-time that contracts space ahead of a ship and expands it behind, carrying a pocket of flat calm across the universe at any speed without violating the local cosmic speed limit. It ends as a cascade of impossibilities so thorough, it feels less like an engineering failure and more like a message from the structure of reality itself. 5 independent barriers, each rising from a different branch of physics, converged on the same verdict with a unanimity that no proposed modification to the metric has ever broken. No single fix addresses them. No combination of advances resolves them. They emerged independently from quantum mechanics, space-time geometry, causal structure, thermodynamics, and the physics of the interstellar medium, yet they aligned with a precision, suggesting they are not separate obstacles at all, but different faces of a single deep prohibition. The universe enforces wherever anything attempts to outrun light. The warp drive fails. That much is clear, but the nature of how it fails reveals something far more profound than the impossibility of one particular technology. It reveals the architecture of the universe itself. To understand what this architecture means, begin with the method that created the warp drive in the first place. The Alcubierre metric was not discovered by studying what matter can do and following the physics forward to its consequences. It was constructed in the opposite direction. Alcubierre wrote down the space-time geometry he wanted, and then asked Einstein's field equations to tell him what kind of matter and energy would produce it. This reverse engineering approach, sometimes called the metric-first method, is a perfectly legitimate mathematical operation within general relativity. The equations run in both directions. You can start with matter and compute geometry, or you can start with geometry and compute matter, but there is a subtle and devastating difference between the two directions. When you start with matter, you begin with something that exists. Stars have been observed, planets have been measured, gas clouds have been mapped. The matter you feed into the equations is real, confirmed by observation, constrained by experiment. The geometry that emerges from the calculation is therefore physically grounded. It describes how the universe actually curves in the presence of the stuff the universe actually contains. When you start with geometry, you begin with a wish. You sketch the space-time shape you desire, the curvature pattern you want to exist, and the equations hand you back a recipe for the matter required to produce it. But that recipe is under no obligation to correspond to anything that exists in nature. The equations do not check whether the ingredients are available on any shelf in the universe. They do not verify that quantum mechanics permits the required energy distribution to exist, let alone to be manufactured. They do not consult thermodynamics, or the stability of the vacuum, or the causal structure of spacetime. They simply compute the stress-energy tensor that would be needed to generate the specified geometry, and they deliver the answer with no commentary on whether the answer is physically meaningful. This is the trap. The mathematics tells you what would work. It does not tell you what is real. It does not even tell you what is possible. It tells you only what is self-consistent, and self-consistency is a far lower bar than physical reality. General relativity is extraordinarily permissive when run in this reverse direction. It generates solution after solution for space-time geometries that have never been observed anywhere in the physical universe. Time loops, unshielded singularities, spatial tunnels, superluminal bubbles, the equations produce them all with equal mathematical serenity. The reverse procedure always follows the same arc. Specify a desired geometry. Compute the required matter. Discover that the matter violates the energy conditions. Discover that nothing resembling it exists in any catalogue of observed particles, fields, or phenomena. Every single product of the metric first method across every research group that has attempted it over 3 decades shares this same terminal feature. The mathematics is always internally consistent. The ingredient list always calls for something the universe does not stock. The equations do not distinguish between the achievable and the imaginary. That distinction belongs to nature, and nature has ruled against every entry on the list. The distinction between mathematical consistency and physical reality is not a technicality. It is the most important distinction in all of theoretical physics, and the warp drive stands squarely on the wrong side of it. The 2026 analysis by Barzagar, Buchert, and Vigneron made this explicit. Their comprehensive classification of warp drive spacetimes found that most proposals in the published literature rely on unjustified simplifications, incomplete calculations, or outright mathematical errors to arrive at conclusions that look favourable. When the full machinery of general relativity is applied without shortcuts, the optimistic claims collapse. The metric-first approach does not produce workable machines. It produces mathematical ghosts, geometries that cast shadows on the equations but have no substance in the physical universe. This brings us to the deepest pattern in the entire story. Every proposed shortcut through spacetime, regardless of design, regardless of originator, regardless of mathematical elegance, runs into the same barrier. Wormholes require exotic matter with negative energy density. Krasnikov tubes require exotic matter with negative energy density. The Alcubierre warp drive requires exotic matter with negative energy density. The Notario warp drive requires it. Every superluminal metric ever published requires it. The requirement is not a coincidence. At power, it is not a shared technical flaw that a better mathematician might fix with a more creative ansatz or a more sophisticated choice of coordinates. It is a structural feature of how general relativity connects spacetime curvature to the speed of light and the ordering of events in time. The Santiago-Schuster-Visser proofs established this with mathematical rigor. The Olam theorem established it with even broader generality. Superluminal motion of any kind, through any mechanism, in any geometry, requires energy that violates the null energy condition. The universe has connected the speed of light to the properties of matter so tightly that you cannot break the speed limit without also breaking the rules that govern what matter is allowed to be. The two constraints are not separate policies enforced by separate authorities. They are aspects of the same underlying structure, two faces of the same architectural principle, reinforcing each other at every level. The energy conditions, those mathematical inequalities that all known matter obeys, are not arbitrary restrictions imposed by conservative physicists. They encode something fundamental about how the universe maintains its logical coherence. The weak energy condition says energy density is never negative. The null energy condition says the energy measured along any light ray is never negative. The dominant energy condition says energy flows respect causality. Together, these conditions protect 3 pillars of physical reality. They protect the positivity of mass, which keeps gravity attractive and prevents matter from repelling itself into chaos. They protect the stability of the vacuum, which keeps empty space from spontaneously erupting into runaway particle production. And they protect the causal structure of spacetime, which ensures that effects follow causes rather than preceding them. Violating the energy conditions does not merely open the door to faster-than-light travel, it opens the door to a universe that no longer functions as a coherent physical system. If negative energy density can exist in bulk, gravitational attraction can reverse. Objects that should fall toward each other would fall away. Space-time geometry becomes unstable, capable of developing runaway distortions that grow without limit. The vacuum can become unstable, decaying into states of ever lower energy in a cascade that would propagate outward at the speed of light, destroying the structure of matter and space as it goes. And causality can break, allowing information to travel backward through time and creating logical paradoxes that have no consistent resolution within any known framework of physics. Imagine a universe where these protections are removed. Causes no longer precede effects. You could receive a message before it was sent, learn the outcome of an experiment before it was performed, remember the future and forget the past. Physical systems could not evolve predictably, because the conditions at one moment would not determine the conditions at the next. Chemistry would cease to function because reactions depend on the forward flow of thermodynamic time. Stars could not burn because fusion requires entropy to increase in the forward direction. Biology could not exist because evolution requires the accumulation of information across generations, which requires a consistent arrow of time. Consciousness itself, which depends on the sequential processing of cause and effect in neural tissue, would become impossible. The energy conditions are not walls around a playground. They are the floor beneath it. Remove them and everything falls. This is why the speed of light matters so much more than any other physical constant. It is not merely the fastest speed. It is the thread that stitches every event in the universe to its consequences. It determines which moments can shape which futures, and which ones are forever beyond each other's influence. It draws the boundary between past and future, between what has already been decided and what remains open, for every observer at every location in the cosmos. Without this boundary, before and after lose their meaning. Without temporal order, physics ceases to make predictions, and science ceases to function. The cosmic speed limit is not a restriction on human ambition. It is the condition that makes an ordered, predictable, habitable universe possible. Every barrier the warp drive encounters is a manifestation of this deeper principle. The exotic matter problem exists because producing negative energy would destabilize the vacuum and violate causality. The horizon problem exists because a superluminal bubble outruns the speed at which control signals propagate, disconnecting cause from effect within the vehicle itself. The causality problem exists because faster-than-light transport, combined with the symmetry of physical law across reference frames, inevitably produces closed time-like curves. The Hawking radiation problem exists because the event horizon created by a superluminal bubble generates thermal emission that destroys the bubble from within. The arrival destruction problem exists because the interaction between the bubble and the interstellar medium concentrates energy at the destination in ways that no shielding can prevent. These are not 5 unrelated failures that happen to afflict the same technology. They are 5 expressions of a single underlying principle, viewed from 5 different angles. The universe protects causality. It protects the ordering of time. It protects the stability of the vacuum. It protects the logical consistency of physical law. And it enforces these protections through every mechanism available to it, through energy conditions, through horizons, through quantum radiation, through the kinematic structure of space-time geometry. Wherever you push against the speed of light, the universe pushes back. And it pushes back not with one force but with all of them simultaneously, as if the prohibition against faster-than-light travel is not a single rule, but a structural property of the entire framework from which rules emerge. Consider what this means for the dream of reaching the stars. Without faster-than-light travel, the interstellar distance problem remains exactly what it was at the beginning of this story. Proxima Centauri sits 4.24 light-years away. The most optimistic propulsion technologies under serious scientific consideration, including laser-driven light sails like those proposed by the Breakthrough Starshot initiative, could potentially accelerate tiny probes weighing only a few grams to 20% of the speed of light. At that velocity, the journey to Proxima Centauri would take roughly 21 years. Data from the probe would then take another 4 years to return to Earth at light speed. A quarter century for a flyby observation of the nearest star, using technology that does not yet exist, carrying a payload too small to include any meaningful scientific instruments beyond a camera and a transmitter. A human crew aboard a larger, heavier vessel, propelled by even the most advanced fusion engine concepts, would face journey times of decades at minimum, centuries or millennia for more realistic designs. Nuclear pulse propulsion, the most energetic subluminal concept ever seriously engineered, could potentially reach a few percent of light speed, putting Proxima Centauri roughly a century away. Generation ships, vessels large enough to sustain a self-reproducing human community for the duration of the transit, would need to function as autonomous civilizations for hundreds of years without resupply, without external communication at useful speeds, without any guarantee that the destination would be habitable upon arrival. These are not exciting numbers. They do not make for dramatic science fiction. A generation ship crawling between stars over lifetimes, carrying a population that might evolve culturally or even biologically during the transit, lacks the appeal of a warp-driven starship arriving at a distant world in days. Robotic probes that transmit data back to Earth over decades of light-speed delay do not satisfy the human longing for exploration, for setting foot on new ground, for breathing alien air. Suspended animation, if it is ever developed for human physiology, introduces its own profound risks and uncertainties, including the question of whether a human mind can survive decades or centuries of metabolic arrest and reawaken intact. These are the only real options the universe actually provides. They are modest, demanding, and slow. They are bounded by the same speed limit that governs every photon, every graviton, every particle of every kind. The universe was not designed for creatures that live 80 years and dream of crossing light years. This is not a complaint or a lamentation. It is a structural observation about the mismatch between human biology and cosmic architecture. The distances between stars are measured in light years. Human lifespans are measured in decades. The mismatch is not a factor of 2 or 10. It is a factor of millions. A civilization that wished to explore even its immediate stellar neighborhood using subluminal travel would need to think in generational timescales, launching missions whose results would be received by descendants who were not yet born when the ship departed. This is the opposite of the warp drive fantasy. It is slow, patient, multi-generational, and deeply uncertain, but it is real. It respects the laws of physics, and it is the only form of interstellar travel that the universe actually allows. Some will find this conclusion disappointing. After 3 decades of research, hundreds of peer-reviewed papers, and headlines declaring that NASA was investigating faster-than-light travel, the answer remains the same one that Einstein's equations gave us in 1905. Nothing travels through space faster than light. No matter how clever the geometry, no matter how elegant the mathematics, no matter how desperately the human imagination reaches for the stars, the cosmic speed limit holds. The warp drive does not circumvent it. It confirms it, because every attempt to circumvent it generates new failures that trace back to the same fundamental prohibition. The loophole was not a loophole at all. It was a deeper room in the same building, with the same rules posted on every wall, but disappointment is the wrong response. The correct response is something closer to awe. Think about what the warp drive story actually revealed. We began with a seemingly impossible distance problem. We discovered that general relativity contains a mathematical loophole, a geometry of spacetime that appears to offer faster-than-light transport. We explored that loophole in extraordinary detail over 3 decades. We refined the mathematics, optimized the geometry, proposed alternative metrics, developed new frameworks for classification and analysis, and at every turn, the universe answered with a deeper revelation about its own structure. The exotic matter barrier revealed that the energy conditions are not arbitrary, but encode the stability of the vacuum and the positivity of mass. The horizon problem revealed that causality is not just a macroscopic convenience, but is enforced at the level of spacetime geometry itself. The causality violation revealed that the speed of light is entangled with the arrow of time in a way that cannot be disentangled without destroying both. The Hawking radiation revealed that quantum mechanics and general relativity conspire to prevent superluminal horizons from surviving. And the arrival destruction revealed that even the interstellar medium, the thin gas between stars that we normally ignore, becomes a weapon when space-time geometry concentrates it. Each failure taught us something we did not know before. Each barrier exposed a connection between different branches of physics that would not have been visible without pushing against the speed of light limit. The warp drive, precisely because it fails, has become one of the most productive thought experiments in modern theoretical physics. It has clarified the relationship between energy conditions and space-time structure. It has motivated new mathematical proofs about the impossibility of superluminal motion under physically realistic conditions. It has sharpened our understanding of how quantum field theory behaves in curved space-time, particularly near horizons. It has forced the physics community to confront the meaning of causality at its most fundamental level and to ask whether chronology protection is a law or a conjecture. It has driven the development of new computational tools, like the warp factory framework, that allow researchers to evaluate thousands of space-time geometries against the energy conditions in ways that were impossible a decade ago. The warp drive failed as a technology. It succeeded as a mirror, and what it reflected back at us was the deepest structure of the universe we inhabit, structure that would have remained hidden if we had never tried to break through it. Here is the final truth that this story has been building toward, and it is not a truth about engines or fuel or bubbles of curved space-time. It is a truth about the nature of the cosmos and our place within it. The frightening part of this story is not that warp drive may be impossible. Plenty of things are impossible. Perpetual motion machines are impossible. Traveling backward through time to change the past is probably impossible. These impossibilities do not disturb us because they feel distant, abstract, disconnected from our desires. The warp drive is different. It feels close. It feels almost within reach. The mathematics works. The equations balance. General relativity permits the geometry. The only thing missing is a substance that does not exist. The impossibility is not remote. It sits one ingredient away from possibility, and that proximity makes it ache in a way that other impossibilities do not. But the deeper fright, the one that lingers after the technical details fade, is what the failure reveals about the universe itself. Our most powerful imagined shortcut, conceived within the framework of our most successful gravitational theory, evaluated using our most advanced mathematical tools, runs into barriers that appear to be permanent, structural, and woven into the foundations of physical reality. These are not walls that a smarter civilization will eventually breach. They are the conditions that make civilization possible in the first place. Without the speed limit, there is no causality. Without causality, there is no arrow of time. Without the arrow of time, there is no thermodynamics. Without thermodynamics, there are no stars, no chemistry, no biology, no minds capable of dreaming about warp drives. The rules that prevent us from reaching the stars are the same rules that created us. We cannot break them without breaking ourselves. This is not a prison. It is a structure, a cage that is also a cradle. The same bars that confine us are the beams that hold the roof over our heads. The cosmic speed limit does not exist to frustrate human ambition. It exists because it is the architectural principle that holds the universe together. Space-time has a shape. That shape determines what is possible and what is not. Faster than light travel falls on the side of what is not, and it falls there for reasons so deeply embedded in the structure of reality that removing them would unmake the reality itself. And yet, the universe that enforces these limits is the same universe that produced beings capable of discovering them. We are made of matter forged in stellar cores, assembled on a rocky planet in the habitable zone of an ordinary star, in an outer arm of an ordinary galaxy. We evolved brains that can grasp relativity, formulate field equations, and analyze warp drive metrics. We developed instruments that detect gravitational waves from colliding black holes, photograph the shadows of event horizons, and map the cosmic microwave background with precision measured in millionths of a degree. We understand, in remarkable detail, why we cannot reach the stars quickly. That understanding is itself extraordinary. No other species on Earth, and perhaps no other species in the observable universe, has ever confronted the cosmic speed limit and grasped why it is there. We see the barrier. We understand its mathematical structure. We feel its emotional weight. We have traced its connections to energy, to causality, to quantum mechanics, to the arrow of time. And we know, with the precision of mathematical proof and the confirmation of over a century of experimental physics that it is not going away. The stars will remain distant, the galaxy will remain vast, the intergalactic spaces will remain empty beyond comprehension. These are facts about the universe, encoded in the geometry of space-time and the quantum properties of matter, and no amount of human ingenuity will rewrite them. They are not laws we imposed. They are laws we discovered, and discovering a law means accepting that it was there before we arrived and will remain after we are gone. But knowing the true shape of the cage does not diminish the beauty of what the cage contains. We live inside a universe spanning nearly 14 billion years of evolution, 400 billion stars in our galaxy alone, 2 trillion galaxies in the observable volume, and possibly infinite space beyond the cosmic horizon. The distances are real, the barriers are real, and so is the grandeur. The warp drive taught us something about our relationship with the cosmos that we might never have learned otherwise. We learned that the universe is not merely large, it is structured. Its rules are not obstacles to be overcome, but principles that give it form, stability, and coherence. The speed of light is not a wall around a prison. It is the frequency at which reality vibrates. It is the tempo of causality, the rhythm of information transfer, the beat that keeps the symphony of physics in time. Change the tempo, and the music collapses into noise. We are creatures of space-time, woven from its geometry, bound by its rules, staring across distances that those rules enforce. And the warp drive, for all its mathematical beauty, for all its imaginative power, for all the decades of brilliant minds that explored its every implication, ultimately told us what we needed to hear but did not want to accept. The stars are not ours to reach quickly. The galaxy is not ours to cross in a lifetime. The cosmos is not ours to shrink. It is ours to contemplate, to study, to map from afar, and perhaps slowly, painstakingly, over centuries and millennia, to explore one patient step at a time, at speeds the universe permits, across distances it will never shorten. The frightening lesson is not that warp drive fails, it is that even the most brilliant theoretical shortcut we ever imagined, one that lives entirely within the mathematics of our most confirmed gravitational theory, trades the distance problem for deeper problems that strike at the foundations of energy, time, causality, and the survivable order of the cosmos. We did not find a way around the rules. We found the rules themselves, carved into the geometry of space-time, enforced by quantum mechanics, guarded by thermodynamics, and binding on every particle, every photon, and every dreaming mind that the universe has ever produced. The stars are far away. They will stay far away. And the reason they will stay far away is not that we are not clever enough. It is not that we lack funding or willpower or imagination. It is that the fabric from which the universe is woven, the same fabric from which we ourselves are woven, does not stretch that way. It never did. It was never going to. The geometry of space-time, the quantum properties of the vacuum, the thermodynamic arrow of time, the Lorentz structure of causality, all of these converge on the same conclusion with a unanimity that leaves no room for appeal. And in that immovable fact lies not defeat, but the deepest kind of knowledge available to a conscious being. The knowledge of where we stand in a cosmos whose structure is grander, deeper, more interconnected, and more unbreakable than any shortcut we will ever imagine. We are inside that structure. We are made of it. We cannot step outside it any more than a wave can step outside the ocean, and staring across the distances that structure enforces towards stars we may never reach is not a confession of failure. It is the view from inside a universe that was never going to bend to our convenience, because its shape is what made us possible in the first place.